This is chapter 20, part 2, capacitance. And we're going to learn about a device called a capacitor, which is something that discharges electrical power very quickly, but is often charged slowly, kind of like filling up a water tank with a trickle and then letting it all come out by tipping the tank over. It's kind of analogous to how a capacitor works, and we're going to learn about it, what it's used for, and how much energy it can deliver. The most famous example of a capacitor is the flux capacitor. Now, this is purely fictional, of course, but it's from the classic movie Back to the Future. And the flux capacitor was invented by Doc Brown to allow time travel in his DeLorean. So just for fun, we're going to watch a little clip from that movie, and then we'll get down to business.
You see, Einstein has just become the world's first time traveler. I sent him into the future. 1 minute into the future, to be exact. And precisely 1:21 a.m. in 0 seconds, we shall catch up with him in the time machine.
Wait a minute, Doc. Are you telling me that you built a time machine out of a DeLorean?
The way I see it, if you're gonna build a time machine into a car, why not do it with some style? Besides, the stainless steel construction made the flux dispersal. Look out!
What, is it hot?
It's cold, damn cold. Einstein, you little devil! Einstein's clock is exactly 1 minute behind mine and still ticking.
He's all right.
He's fine, and he's completely unaware that anything happened. As far as he's concerned, the trip was instantaneous. That's why his watch is exactly 1 minute behind mine. He skipped over that minute to instantly arrive at this moment in time. Come here. I'll show you how it works. All right. First, you turn the time circuits on. This readout tells you where you're going. This one tells you where you are. This one tells you where you were. You input your destination time on this keypad. Say you want to see the signing of the Declaration of Independence. Or witness the birth of Christ. Here's a red letter date in the history of science, November 5th, 1955. Yes, of course, November 5th, 1955.
Why, I don't get what happened.
That was the day I invented time travel. I remember it vividly. I was standing on the edge of my toilet, hanging a clock. The porcelain was wet. I slipped, hit my head on the edge of the sink, and when I came to, I had a revelation, a vision, a picture in my head, a picture of this. This is what makes time travel possible. The flux capacitor.
Flux capacitor?
It's taken me almost 30 years of my entire family fortune to realize the vision of that day. My God, has it been that long?
I'd like to tell you the story of an accident that happened to a certain Professor Muschenbroek. At the University of Leiden in the year 1745. It was believed at the time that electricity might be a kind of fluid, and Muschenbroek wanted to make a solution of the electric fluid with ordinary water. And so a friend of his named Andreas Cuneus, who acted as his assistant, took a jar of water like this in his hand and put into it a stopper with a long nail in it. Then he held the nail up to the pole of an electrostatic generating machine, something like that one, so that the electric fluid could run down the nail into the water and make a solution with it. And then, when he grabbed the nail to pull it out of the water, he made an absolutely shocking discovery. Muschenbroek wasn't deterred at all. He just found himself another volunteer and went on with his research. But that discovery, which came to be known as the Leyden jar, turned out to be one of the most important of the 18th century. Because before it, electricity was a mere curiosity. But afterward, it became something genuinely powerful. To appreciate the impact that the discovery had at the time, you have to understand something about the way science was done. People who did experiments on electricity, they were called electricians, formed a kind of fraternity. And like any fraternity, it had its rules and its rituals. Now, there were crude instruments at the time that could measure the amount of electricity that had been produced. But every electrician prided himself on his ability to judge the strength of the electricity by feeling the shock that it produced. It was something like a chef tasting the soup. No electrician would think of sending an experiment out without first feeling the shock. Well, before the discovery of the Leyden jar, that was harmless. But afterwards, it was an entirely different matter. It was not a good time to be an electrician. Muschenbroek himself was the first one to do it, and he later wrote to a friend that he wouldn't do it again for all the kingdom of France. Nevertheless, every electrician had to feel the shock, with one exception, a German electrician named Winkler, who gallantly permitted his wife to do it for him. It turned out that Leyden jars were very easy to make, but it was very difficult to understand why they worked.
Sometimes there isn't enough electrical energy available for a particular need. Capacitors are used to store energy for future use. And that's because sometimes you need sudden bursts of power. And so you kind of save up the charge for a later time. A capacitor, old-fashioned name is condenser, is a device used to store electrical energy. They accumulate and store energy for later use. It's like saving your pennies in a piggy bank for a large future purchase. You can't buy something for a penny, but if you save up enough pennies, one day you'll have many dollars. The symbol for a capacitor in circuit diagrams, which we'll get to later, is this symbol, a line, two parallel lines, and another line perpendicular to that. Capacitor construction. A capacitor consists of two separated conductive plates connected to an electric potential difference. Positive charge builds up on one plate, negative charge builds up on the other. So here we have a battery connected to two parallel plates, and you can see the negative charge building up on the right, positive charge building up on the left. They balance each other out, and that charge just sits there until it's needed. Capacitors, they consist of two conducting plates of area A separated by a distance d. Now, in previous sections, since we started on electricity, you've seen parallel plates, especially when we talk about uniform electric fields. And sure enough, the electric field created within a parallel plate capacitor is a uniform electric field. Today we're going to learn more about what capacitors do and how they work. Now, a capacitor's function is to store large amounts of charge to be released when needed. And that's because for some applications and some instruments, you need a sudden burst of power. And so the capacitor stores that power up until you need it. Think of it as a big water tank. If you fill a water tank all the way up, it creates a lot of pressure on the bottom. But you can fill it up with a trickle. As long as that trickle is constant, once in a while you can draw from the bottom. It's the same type of thing with capacitors. They are charged slowly, but discharged quickly. Now, positive charge is stored on one plate, negative on the other.
The charge stored in a capacitor. The amount of charge a particular capacitor can store depends on the voltage and the rating or capacitance of the particular capacitor. Let's take a look at capacitance. Capacitance is defined as the ratio of stored charge to potential difference. And that's why C for capacitance equals Q over delta V. Now, the unit for capacitance is the coulomb per volt, but most people don't talk about coulombs per volt. It's very unusual, and so you should get used to just calling this a farad. Now, the farad is named after Michael Faraday. He was a 19th century English physicist and chemist who made several important discoveries in electricity and magnetism. He also was the first to visualize the electric field as a set of directed lines. So this whole thing about drawing field lines and the fact that they're drawn from positive to negative, that started with Faraday. Now, Faraday was a pretty amazing guy because he was from a poor family. He received very little schooling, and he wasn't even able to take higher math like trig or calculus. He was just a natural scientific genius, and he was a great experimenter. He did all kinds of experiments. He was thorough about them, careful, kept good records, and he had brilliant insights. And he did all that without much formal training and with very little math background. So Faraday, he was actually one of Einstein's heroes. Einstein kept a picture of him up in front of his desk. Faraday invented the first electric motor. He also discovered something called electromagnetic induction, which shows that a changing magnetic field produces an electric current. And following that discovery, he invented the first electric generator, which is the basis for all modern day generators. 1 farad. 1 farad would be a particularly large capacitor. This would be large in physical size and charge storage. Most capacitors are much smaller. And they are usually in units of microfarads, or μF. And remember that micro means 10 to the negative 6, or 1/millionth of. So one microfarad equals 1/millionth of a farad. All right, so let's look at an example of charge storage. How much charge is stored in a 100 microfarad capacitor that is connected to a 12-volt battery, an electric potential source? All right, so pause the video, do this on your own, and resume when you have an answer. All right, so let's go through the solution. Let's write our givens down. C equals 100 times 10 to the negative 6 farads. Delta V equals 12 volts. And we're trying to find Q. So we use C equals Q over delta V. And then we just do our plugging and chugging. Put in our given values and find Q, which is 1.2 times 10 to the negative 3rd coulombs. And that, of course, is the same as 1.2 millicoulombs. Micro is the mu. Milli is the little m. And when you see the little m, you know that you're dealing with the negative 3 power. When you see the mu, the Greek mu, you know that it's micro and you're dealing with the negative 6 power. And when you see the little n, it's nano, and you're dealing with the negative 9th power.
An ordinary battery has the potential to create an electric field.
When a battery is connected between two pieces of metal, it forces charge to flow from one to the other until the potential difference between them is equal to the voltage of the battery. That creates an electric field between them. If the voltage is doubled, so is the charge. So is the potential difference. And so is the electric field. In general, the charge transferred is proportional to the voltage applied, and the constant of proportionality, C, is called the capacitance.
Long before there was a modern capacitor, much less the means and mathematics to illustrate how one works. Everyone in the world knew about lightning. But to discover the role of lightning in the world of natural science, one had to follow Ben Franklin into the study of electricity itself. Of all the 18th century electricians, only Franklin had seen lightning bolts for what they are, huge sparks of electricity, no different from the kind he could create in his laboratory. On paper, there was the basis of his theory. First, extend a metal pole, the lightning rod, from the roof of a building. Then, place a wire near the rod. In theory, the rod would draw some electricity from the stormy sky, and a spark would jump from the metal to the wire. Prior to the experiment, these instructions had been printed in England. Thomas Francois d'Albert had followed them to the letter and successfully performed the experiment on the outskirts of Paris. Of course, Franklin had no way of knowing that, as he himself stood up to face the power of Mother Nature. And in any case, when it came time to put his own theory into practice, he'd done so in a far more dangerous manner. Instead of using a lightning rod to draw electricity from the sky, he used a kite, a simple apparatus made of twigs and a silk handkerchief. And instead of a separate wire, he attached a metal key to the kite string. On the fateful night, he noticed loose threads standing out from the kite string. Then, just as he had bravely predicted, the sparks jumped. And as they zipped from the key directly to his bare knuckle, Franklin experienced a feeling he'd never forget. But in fact, Franklin's greatest discovery was not made with lightning bolts. It was made with Leyden jars. And it was here, rather than in the stormy sky, that Ben Franklin revolutionized the science of physics. Others assumed that when they charged a jar with electricity, they were adding large amounts of electricity to it. But Franklin knew better. And with his knowledge, he was the first to figure out how a capacitor worked. He realized that the electric fluid was neither being created nor destroyed. It was merely flowing from one place to another. In a Leyden jar, it was flowing from the conductor inside the jar to the conductor on the outside. In other words, the Leyden jar was the first primitive electric capacitor.
Any two pieces of metal can form a capacitor. The shape doesn't matter. The two pieces of metal can be the plates of a parallel plate capacitor, or they can be the inner and outer parts of a Leyden jar.
The electric field in a parallel plate capacitor is really due to sheets of opposite charge facing each other on the metal surfaces. The field between the sheets is constant. The two sheets of opposite charge attract each other and hold each other in place. That's why a capacitor is such a useful device. If the voltage is held constant by a battery, the charge, and therefore the capacitance, changes inversely as the distance between the plates, and is proportional to the area of the plates. And only Ben Franklin realized that it didn't take a fancy Leyden jar to hold on to electricity. A simple pair of parallel metal plates would do. Despite its occasional inaccuracies, Franklin's work with electricity was a scientific milestone. But even so, Ben Franklin will always be best remembered as a statesman and a remarkable public servant. Here in Philadelphia, he established the first public hospital, the first public library, and the first fire department. As a delegate to the Albany Congress of 1754, he had been so bold as to propose a union of the colonies. For almost countless reasons, Benjamin Franklin was and is a national treasure, a monument to the limitless promise of democracy. In this room, with the diligence of a scholar and the moderation of a statesman, he set the course and molded the ideals for a newborn nation.
So capacitance is affected by changing the area of the plates or the distance between them, such that C equals EOA over D. Now, don't worry about the EO for now. I'll get to that a little bit later. But for now, what's important to realize in this equation is that the capacitance varies directly as the area and inversely as the distance. Now, what does that mean? It just means that if area goes up, capacitance goes up. If area goes down, capacitance goes down. And we can see that since area is in the numerator, if you make your numerator higher, well, then the whole thing becomes higher. Now, capacitance varies inversely as distance, and what that means is that if the distance goes down, the capacitance goes up. If the distance goes up, the capacitance goes down. And that's why D is in the denominator. As you remember, if the denominator gets big, then the whole number gets small. If the denominator gets small, then the whole number gets big. All right, so this equation just formalizes or shows in mathematical form the dependence between distance and capacitance and between area of the plates and capacitance. Now, EO is called the permittivity of free space, and it is a constant, 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. A few things regarding this constant. First of all, you don't have to memorize it because, I'll give it to you if you ever need it, especially on a test. It is a constant of variation, just as we've seen with big G and gravitation, and we've seen it with K in the electric force. And EO is actually related to K. We don't have to get into that relation here. But the important thing to remember is it's just a constant, okay? And you can think of it as a constant of proportionality that's thrown in here to show the direct variation of C with A and the inverse variation of C with D. Now, what is permittivity? Permittivity comes from the Latin permittere, right? To send through. And so permittere refers to, or permittivity rather, refers to the ability of a medium to have or facilitate electric fields within it. Okay, now this also refers to the ability of a medium itself, a material itself, to set up its own electric field. Now, obviously, when you're dealing with a vacuum, free space, vacuums can just have electric fields go through them, but since they contain nothing, they can't actually have atoms inside them that set up their own electric fields. And so free space is actually the lowest permittivity. When you throw stuff in there, you actually raise the permittivity because you have atoms that can polarize and create their own electric fields. Now, I'll explain what I mean by that in just a little bit. But for now, just realize what permittivity refers to the ability of electric fields to go through a substance or a medium, and in this case free space is a vacuum, so it's like a non-medium, but it's what is between the plates. All right, it refers to the electric field that can go through what's between the plates. Now, you don't have to worry about all that explanation stuff. It's just for your own interest. But permittivity of free space is a constant. And it's a reference constant, just kind of like that threshold of hearing one that we saw when we were doing sound. 10 to the negative 12 was our threshold of hearing. And so the same thing is true here. This is kind of a lower threshold of permittivity. Now, the permittivity of air is almost the same. And so if you ever get to a problem where they're talking about a vacuum between these plates or air between the plates, you're going to use the same constant of 8.85 times 10 to the negative 12. Increasing area. So as we already learned, to have a more powerful capacitor, you would want a larger area. However, that may be impractical. It might take up too much space. So some capacitors are rolled to maximize space. This gives the typical round or cylindrical shape of capacitors. So if you open up an electronic device that uses a capacitor, normally you're going to see this shape instead of the standard parallel plate shape, just because if you have an inner conductor and an outer conductor, you are able to maximize space. A dielectric is a material that enhances the capacity of a capacitor. And capacity is just a synonym for capacitance. Often an insulating material is inserted between the plates of a capacitor. This substance is called a dielectric. Now here we have two plates of a capacitor, positive and negative, and we see a dielectric material in the middle of them. Dielectrics resist charge flow more than air or empty space. Thus, higher voltages can be applied before the charge jumps or discharges, thus more capacitance. And that, of course, means that more charge can be built up on the plates. Capacitors and dielectrics. When placed between the plates of a capacitor, a dielectric gives a lower potential difference with the same charge, due to the polarization of the material. This increases the capacitance. Alright, now it might not be readily apparent why this is true. So just let me quickly explain that. Okay, so why does a dielectric increase capacitance? Well, let's look at why here. In the last diagram, we saw how the atoms of the dielectric material become polarized. Alright, so overall what's going on here is that we have more negative charge gathered on the left side of the dielectric and more positive charge gathered on the right side. And what that sets up is an internal E field. Now I've got a little red vector here marked ED, just referring to the electric field of the dielectric material itself. And I have a big red vector here, EC, which refers to the overall electric field of the capacitor. Now, big EC is referring to the field lines that go from the positives on the left plate to the negatives on the right plate. Little ED is referring to the little field lines that go from the buildup of positives on the right part of the dielectric to the buildup of negatives on the left part of the dielectric. So as you can see here, little ED is opposing big EC, which is going to decrease from the overall electric field. Now we know that delta V equals ED, and so we can see that if E goes down, delta V goes down, right? Because this is a direct relationship. If E gets small, delta V gets small. If E gets big, delta V gets big. Alright, so E is going to get smaller here because the little ED vector is opposing the big EC vector, thereby decreasing the overall electric field. Now we also know that the capacitance equals the total charge divided by the potential difference, or Q over delta V. Okay, so now let's put this together. The net electric field of the capacitor is decreased. I already explained that, and that's because ED is opposing EC. Therefore, the potential difference is smaller and the capacitance is larger. Now, why is the potential difference smaller? Well, because the E is smaller. And why is the capacitance larger? Because if delta V is smaller, then C, or capacitance, gets bigger. Alright? Inverse relationship. If delta V gets smaller, as we've seen that it does, then the C, or capacitance, gets bigger. And this is precisely why dielectric materials increase capacitance. Now, with a dielectric instead of air between the plates of a capacitor, the plates can be placed closer together, thus more capacitance. Because of the presence of the dielectric, capacitance is increased. It's increased by a dielectric constant K, which describes the factor of additional capacitance. Now, this dielectric constant is sometimes called the relative permittivity, but dielectric constant is the term that we're going to prefer. So now let's talk about the dielectric constant K. Sometimes it is included in the capacitance formula that I already gave you, which was C equals EOA over D. Here all we have is that same formula that was already highlighted, so I'm not going to highlight it again. It's just that K is here, and the K shows that the capacitance is affected, enhanced by the dielectric constant. So these are all the elements of the formula when it includes K. Now I know it's sometimes irritating that one symbol can stand for several realities. And here, of course, we see that K can be the electric constant, 8.9 times 10 to the 9th, or it can be this one. You just can tell by context. All right, let's do this problem. A parallel plate capacitor has a capacitance of 5 times 10 to the negative 6 farads when filled with a dielectric. The area of each plate is 1.7 square meters, and the separation between them is 1 times 10 to the negative 5th meters. What is the dielectric constant of that material? Okay, so pause the video, do this on your own, and resume when you have your answer. All right, let's go through the solution. We're going to use the equation C, or capacitance, equals K EOA over D. And we can rearrange for K, and that's going to give us an expression that has K on the left, and that is K equals CD over EOA. And now it's just a matter of plugging in what we know, putting in the givens, and then doing the calculation. So when we put in all the givens from the problem, we end up with 3.3 as our dielectric constant K. Now there are no units because the dielectric constant has no units. It's simply a measure of relative permittivity, and it's simply a scalar number that shows how high or low the permittivity of a dielectric is in relation to the permittivity of free space, which is the standard by which all permittivities are measured. And so K just shows how poorly or well something functions as a dielectric. And so the final answer with the proper number of significant digits is 3.
This is a table of common dielectric constants. And notice that the symbol here used is kappa, or the Greek lowercase k. And you don't have to worry about using that or distinguishing it. The only reason they did it here is because they want to set it apart from the electric force constant K that you already learned. In any case, what we can see here is that the dielectric constant is a property of the material. In other words, different materials have higher or lower dielectric constants depending on their properties. Let's look at the bottom of the table, and we see that a pure vacuum has a dielectric constant of 1. And of course, you know, if you just multiply 1 by EO, you get EO, and that's why when we use the formula C equals EOA over D for vacuum or for air, we didn't have to worry about the K. Now air is 1.00059, which is so close to 1 that for all practical purposes we can just treat it as 1. Now going up the table, we see that we have higher and higher dielectric constants. And that's because these materials have higher and higher permittivities. In other words, that means that their atoms, their molecules, polarize easier. If they polarize easier, you're going to get more internal electric field, and that will oppose the overall field. And that's precisely what makes the dielectric constant high. Now notice how high the dielectric constant of water is, 80.4. It's huge. And that's because water polarizes so well, and so it sets up a strong internal electric field when it is used as a dielectric.
Alright, so let's look at this animation and see what happens to the capacitance when we adjust the separation, the plate area. And then after that we'll put in the dielectric and see what effect that has. Alright, so here we have a capacitor hooked up to a standard 1.5 volt battery. We can see the positive charge accumulated on the top plate, negative charge accumulated on the bottom plate. First let's see what happens with the separation. Remember, if capacitance is inversely related to separation, then that means if separation goes down, capacitance should go up. Let's see if that's true. Right now the capacitance is at 1.10 times 10 to the negative 13th farads. So if we decrease the separation, just as expected, the capacitance has gone up to 1.77 times 10 to the negative 13th farads. All right, now let's see what happens if we increase the plate area. If we increase the plate area, keeping in mind that capacitance is directly related to plate area, well then we should get a higher capacitance with a higher plate area. Let's see if that's true. So I increase the plate area, and sure enough, the capacitance is increasing. And so now I'm at 2.97 times 10 to the negative 13th farads. All right, now let's see what effect inserting a dielectric will have. The dielectric material we're going to start with is Teflon, which has a K, or dielectric constant, of 2.1. And so, of course, that means that it is 2.1 more permittive, if you're referring to the permittivity. It's 2.1 more permittive of electric fields than free space is. All right, so let's see what happens when we put the 2.1 permittive Teflon into this capacitor. Now keep an eye on the capacitance. Right now it's at 2.97. See what happens when I stick this meat into the sandwich. And what we see is a much higher capacitance. We're now at 6.24 times 10 to the negative 13th farads. It's made a big difference. We can also see that there's a lot more positive charge on the top plate, and certainly more positive charge, or negative charge, sorry, on the bottom plate. And we can also look inside the dielectric and see that it has been polarized. And so we've got some negative charge within the dielectric, kind of moving up towards the top, and we have some positive charge in the dielectric that's kind of moving down towards the bottom because it's attracted to the negative plate. And that polarization, as explained earlier, is creating an internal electric field that opposes the capacitor's field, and thereby it is increasing the capacitance because it's also giving you a lower potential difference. And as we talked about before, that's going to help increase the capacitance. A lower potential difference is a result of a lower field, and that's going to give us a higher capacitance. Okay, now let's see what happens with a different dielectric material. We're going to take this meat out of the sandwich. We're going to replace it with paper. As you can see, paper has a higher dielectric constant than Teflon. And so paper would be 3.5 more times more permittive than free space or air. And that's what the 3.5 means. So, okay, let's change it to paper. And now we're going to put this paper meat into the sandwich. And let's see what happens there. Remember, it's at 2.97 times 10 to the negative 13th farads now. Completing the sandwich gives us a much higher capacitance of 10.40 times 10 to the negative 13th farads. Once again, looking inside the dielectric, we can see the polarization, the separation of negative and positive charges, thereby increasing the capacitance for the reasons explained earlier. Okay, now let's talk about discharging a capacitor. We already know that a capacitor fills up while electrons are being deposited onto one of the plates. But the capacitor can be discharged if the two plates are connected. Usually a switch is used for that. Now the whole point of having a capacitor is for the discharge. You know, what's the point in saving pennies up in the piggy bank unless you use them? This causes all the accumulated electrons to suddenly flow back. And this movement of charge can be used. It's used to do work. It's used when you need a sudden burst of energy. So here's a diagram that shows discharging. When you close the switch, let's say we're going to close the switch of an already charged capacitor. We disconnected it from the battery. Now we're going to switch it so that it can temporarily power this light bulb. Okay, so we've got the circuit here. We close the switch, and when we do that, the electrons start flowing through the circuit, powering the light bulb, from the negatively charged plate to the positively charged plate until all the charge has been used up. Notice how the charged capacitor can temporarily power the light bulb as it is discharged. Again, the whole point of having capacitors is for the discharge. The buildup of charge is preparing for the discharge. Now, what are the uses of capacitors? In the flash of a camera, charge is stored by a capacitor until needed. Flash. That's why if you take a flash picture, you often need to wait a little bit until you can use the flash again, because the capacitor has to recharge, the capacitor that drives the flash bulb. It needs time to recharge. Another Hollywood type example of the use of capacitors is Iron Man. You know, Iron Man has an energy cannon in his palm, the base of his palm, and when he wants to fire it at an enemy, he just directs his palm towards the enemy and boom. But notice that he doesn't just shoot one shot after another. There's a certain amount of charging time between shots, and you can even hear it in the movie. Just before the shot, you hear that kind of and then another one, and that's the charging time. And that little sound effect they have there is his supercapacitor charging so that it can discharge and power the energy cannon. Okay, so even Hollywood makes use of capacitors. In this case, that's a more realistic use of capacitors, unlike what I showed you in the beginning of the video with Doc Brown and his flux capacitor. So an analogy for discharges. Imagine a stream gradually running into and filling a dam, which would be like a capacitor. The water, or the charge, accumulates until it is released, discharged. That would be like the dam bursting, and all that water goes gushing forth. That's what a capacitor discharge is like. Alright, we're going to watch a quick animation of a capacitor charging. And the main thing to notice is that the charges move quickly to the plates in the beginning, because at that time it's easy to charge the plates. But towards the end of the charging process, the charges move more slowly because it's requiring more work to move them. And that's because each plate already has a certain amount of charge built up. And moving electrons to an already negatively charged plate becomes harder and harder as time goes on. Now I'm going to show you this animation as an introduction to the concept of energy in capacitors. So just observe how the charge builds up quickly at first and then slowly. So notice that the charges are moving quickly at first and the charge is building up quickly on the plate, but the charges keep moving more and more slowly because it's harder and harder to charge an already negatively charged plate. And so the last electron is going to move the most slowly because it's requiring the most work being done by the battery to move it to an already negatively charged plate. Now let's look again at the same thing. On the right we have a graph of charge versus time. Notice that the graph is steep at first, but as time moves on and as the capacitor approaches its maximum charge, the rate of charging levels off. And so we can see that a very little amount of work is required to charge the capacitor in the beginning, but more is required at the end. Okay, now we're going to derive an expression for the potential energy of a capacitor. And first, let's see what is the work done in charging a capacitor. Now, we already saw in the animation that when the point charges first arrive to the plates, they arrive unopposed. But as more and more point charges build up on the capacitor plates, it requires more and more work to deposit more charges there. Alright, if the electrons arrive at an already negatively charged plate, it's harder because, they're already being repulsed. So let's look at the overall work done in charging a capacitor by looking first at the work done in moving each little charge. Okay, so recall that delta V equals delta PE over QO, and that equals W, or work, over QO. And we know that already from the last section. Okay, so we're going to think of QO as the little bitty charges that are getting deposited on a capacitor plate. until the overall charge of big Q is reached. Okay, so the work for each of these little charges is QO delta V. Now, if we are looking at the overall work, or the net work, in charging the whole capacitor, we have to keep putting little QOs onto a plate until the overall big Q is reached. And that's going to involve an average potential difference, simply because in the beginning, when there's very little charge on the plates, there's very little potential difference between them. As more and more charge builds up on the plates, more and more potential difference also builds up between them. Okay, so we have our overall work equals the overall charge times the average potential difference. And that average potential difference is looking at what each little charge experiences from 0 to the total delta V. And so what we can do is we can rewrite the delta VAV as delta VI initial plus delta VF final over 2. And that recalls some of those equations from way back in chapter 3, the average velocity equation. You know, if you start out at 0, end up with a certain velocity, you can find the average velocity. Well, a similar thing is true here. We are starting out with a delta VI of 0, and that's why we put 0 in there, because the initial potential difference is 0. But we're going to end up with a final potential difference, or delta V, that matches the delta V of the entire capacitor. So we can rewrite it this way, and we have our network equals 1/2 big Q delta V. Big Q is the overall charge on the fully charged capacitor, and delta V is the overall potential difference. So that finally leaves us with our equation for the potential energy of a capacitor. And I did highlight this because, as always, the derivations aren't highlighted, just the final equation. That's really all that you're responsible for. So electrical PE of a capacitor, all right, this is specifically for a capacitor, equals 1/2 Q delta V. Now, the reason this is written as just PEE instead of delta PEE, in case you were wondering, because remember that delta PE is always work, and work is always delta PE. Work can sometimes be delta KE as well. It doesn't matter. Work is a change in energy. But we're just skipping the delta here because we know that we started at 0. And so when you start at 0, the delta of whatever quantity you're talking about just equals the overall quantity. Okay, so we've got this expression for the potential energy of a capacitor. Now we're going to derive quickly 2 other expressions that really just come from this equation. And so if you prefer, you can derive them on the fly whenever you need them, or you might prefer to just memorize all 3. It's up to you. Okay, so let's derive one of the corollaries of this, and we have the C, or capacitance, equals the total charge over the potential difference of the capacitor, and then that can be rewritten as Q equals C delta V. And then finally that leaves us by substitution with electrical PE equals 1/2 C delta V squared. Now another corollary uses the same fact, that C, or capacitance, equals Q over delta V. And now we can solve for the delta V and get delta V equals Q over C. And we can put that in the original equation and have electrical PE equals Q squared over 2C. Now, as you can see, really the only important equation is PE equals 1/2 Q delta V. The other ones are just corollaries. So either derive those whenever you need them or memorize them. But highlighted on this screen are the 3 equations for the potential energy of a capacitor. Let's take a look at this problem. A booming car stereo uses a 0.95 farad capacitor connected to a 12-volt battery to supply the frequent bursts of power that the battery by itself can't provide, especially for loud bass notes. How much electrical potential energy does this capacitor hold? Alright, so if you've ever been in a car with the booming bass speakers, or you've been next to one, you know what kind of power they have. Well, that kind of power just can't come from a 12-volt battery, and so car stereo systems need they need to make use of capacitors. Now, if you look at this schematic diagram, and when we get to circuits, you'll see diagrams like this. They simplify the wiring. And what we have here in the blue rectangle is a capacitor, and that's a model of a cylindrical capacitor. That's the most common type. Most capacitors are cylindrical just because it's more efficient to wrap the inner conductor inside the outer conductor with a dielectric in between them. Alright, so pause the video, do this on your own, and resume when you have an answer. Let's take a look at the solution. We know the capacitance is 0.95 farads. The potential difference, or voltage, is 12, and we want to find the electrical potential energy. So we use PE equals 1/2 C delta V squared. We plug in our givens, and we end up with 68 joules.
This is classwork. We are now at the last section before a test, and what we're going to do for this test and the remaining tests of the semester is when we get to a last section, those problems will be absorbed into the review problems sheet, and I'll be giving you that sheet later. See you in class.